Okay, so right. So I wanted this to basically be a time where we could dive into the Rust profiler code and actually take a look at it, because I figure there are going to be people besides me who want to modify it at some point. So yeah, so definitely feel free to stop and ask questions. So I figured, since a lot of people are probably new to Rust, I would walk through sort of a short Rust overview first. And then I was going to basically do a tour through the code base. But if anyone else, has any ideas, please let me know what you want to see, because this is mostly for you. Okay. Right, so starting with sort of Rust 101, this is sort of the Hello World program in Rust. So it mostly looks pretty familiar if you're coming from C++. The main things are it has a function keyword. So I think the general principle with Rust keywords are if there's an equivalent keyword in C++, then it will be the same. So you write return as return. But if it is not in C++, then it's generally going to be shortened. So fn is the function keyword. Right, don't need to stress too much about printing because that's not really the focus of what we're doing. But anyway, that's how you print. So you can create variables with let. And again, there is a keyword for it. And one thing to note here is that Rust does type inference. It only does it locally. So we'll get to this in a second, but when you have a function declaration, you always write out all the types in your function declarations. So this is not Haskell. So you don't write, whole programs without types, but typically, within the scope of a function, then you'll typically leave out the types. So here's a simple example with a data structure. So we're going to create a vec, which is basically like standard vector on the first line here. And notice that we made this a mutable variable. So by default, variables are not mutable. And so you have to explicitly mark them mutable if you want to change them. So we push two things in, and then we're going to loop it. So for every element in the vector, we do something with it. One thing to watch out for, this sort of gets very quickly into what is different about Rust. This is a loop that consumes the vector. That means basically at the end of the loop, this vector is no longer valid. And so if you try to push again after this, that's going to give you a compile error. And one of the nice things about Rust is that it actually tracks this at compile time. There is compile time logic that tracks this. So this isn't a runtime error, this is a compile time error. Okay, but that's probably not what you intended to do here. So typically what you would do is if you don't want to consume it, you would want to borrow using this ampersand operator. And then the vector continues to be valid afterwards. So that's sort of one of the key things about Rust, one of the, the innovations and the nice things is that it tracks the way that data is used. And there's this difference between consuming an object and just borrowing it. And so everything that you do in Rust, you need to think about how are you using the data, right? But sort of the bonus that this gives you, is there's just like a whole class of memory errors you just can't get. Let's see here. Yeah, so I see a question in the chat about the ampersand being on the X rather than the element. So, right. So the way Rust works, basically okay, there. Sorry, my interface is glitching. Right. Okay. Right. When you have a reference to something and you iterate it, that turns into an iterator on references of the elements. So there's a bunch of, one of the things that can be a little bit tricky about Rust code is knowing that there are some automatic conversions. And because Rust is a safe language, you can't really shoot yourself in the foot that way. But there is stuff that happens behind the scenes, right? So again, yeah, reference to object when you iterate it, turns into iterator on the references of the elements of the object. Okay, so like I mentioned before, here are a bunch of functions, right? You use this colon to define the type. So again, it's sort of opposite of C++, but if you're used to type theory, very familiar syntax. And one of the things about Rust is that there are no, with one exception, there are no sort of system specific types. So it's all explicit. So you have I8, I16, I32, I64. So you always specify the bit width of your types. And if you have like a vector of something, you're going to specify, what it's a vector of, right? As opposed to my code earlier, right? This was type inferred, right? That's a vector of int of I32, but I didn't specify that. And again, you have to be careful, what you're writing here. So in F2 here, that's going to take the object and consume it. So at the end of F2, it's going to be destroyed. F3 is going to take a reference. And one of the important things about this is that the reference cannot outlive the call to a first approximation. You can do fancy things if you want to, but the general idea with this is it's going to follow a stack discipline, right? So if you pass a reference into a call, you can't just go and stuff it in some global data structure because that's not going to be valid. And so that the reference tracker is smart enough to catch dangling pointers. So it will prevent dangling pointers here. And then F4 is the mutable version of that. So, I mean, one of the nice things about this is just looking at the function signature here, you can tell, I mean, F3 is effectively the equivalent of const in C++. And F4 is sort of the explicitly mutable version. Okay, so, and again, please feel free to stop me if I'm going too fast. So Rust has structs, and they work pretty much like you'd expect, except the one big thing is they do not have methods. So this is not a C++ type thing where your data and your methods are sort of grouped together. Data and methods are separate. Okay, so in Rust, we have this struct f, which has a field on it. And then when we can have methods, in this case, we're going to implement something on f. This is just going to be sort of a freestanding method. And there are multiple ways to do it. But anyway, this is one of the ways. And so this is a method, if you're used to Python, that's the self parameter in the first slot. That's like your this object in C++. And second parameter is whatever you want. And so then if we have some other code, we're going to take this object f and call some method on it. You do that with sort of the traditional syntax. But again, I mean, one of the nice things about it is anybody can implement these methods wherever they want. So, if you're taking, there's a library with some struct in it, you want a method just randomly in your code, and you're not the library that implemented that struct in the first place, you can add methods wherever you want because the methods are not associated directly with the struct. But there is sort of, and the other sort of big thing that you can do with Rust is called a trait, which if you're thinking about this, you should really replace this with interface. So if you're used to interfaces in Java, C++ doesn't really have them. But anyway, maybe in C++ 20. But anyway, so a trait gives you a set of methods that are going to be defined. So anything that implements this trait T has this method f on it. But it doesn't tell you what type that thing is, right? So we could, suppose we have that struct from before, we can implement the trait for that struct by basically writing out the code in this middle impl block here. And then when we have code later, this is sort of what generic Rust code looks like down at the bottom here. So this is a function. It takes a generic parameter u, which is going to be some type. It has one parameter of that type. And then at the end, this where clause gives you the bounds on that type. So you must implement this trait T. So basically says you use any type such that it implements the trait T. But you can write more sophisticated things down in there if you want.
So the trait is like a type class in Haskell?
Yes.
Okay.
Yes, right. If you're familiar with type classes, they are extremely similar, including the orphan rule. If you're familiar with that, basically, one of the rules with traits is that, so before this impl block I had, you can put that anywhere, right? You can implement that for a library someone else defined. Traits are a little bit different. So with a trait, you can only implement a trait if either the struct is defined in your current, the Rust module is called a crate, so in your current crate, or if the trait, so either the struct or the trait has to be implemented in the current unit that you're coding. And that is sort of for consistency purposes. Okay. So yeah, I mean, so I think at this point, that's sort of the end of the super speedy Rust overview. I guess there's a sort of a couple things, I was going to put here, things to think about, when you're thinking about idiomatic Rust code. So Rust, if you're used to thinking about ownership in C++, Rust is like that on steroids. So Rust has an explicit type system that tracks, all the stuff that you're, might be doing informally in C++, except it's all explicit. So, so everything you're coding in Rust, you always sort of have in the back of your head who owns it, and are you borrowing it? Are you going to consume it? Are you going to mutate it, right? Rust doesn't really have this notion of classes, and so inheritance isn't really a thing. So typically, so some of the organization that we're going to see, because the original profiler code was a very inheritance-driven sort of code base, that means some of that code looks different because that inheritance isn't really a thing in Rust. Again, if you're having classes, you can replace them with traits, but actually a lot of the time you don't even do that because you really only use traits if you want code to be generic. So if you have 2 or 3 things that all implement the same interface, then you use a trait. But if you just want, to implement some methods on a struct, you just stick those methods on the struct and you don't worry about it. Okay, so you think about things a little bit differently. And sort of one of the biggest things and most practical things as far as the profiler is concerned is in Rust, it really encourages you to go with bulk data structures. So you tend not to end up with object graphs, partly because of the mutability. It's just, dealing with analyzing graphs in a compiler is hard. And so Rust sort of pushes you away from that. And so you end up you tend to have, instead of allocating 10 objects and having them hold direct references to each other or whatever, you would tend to make, a vector with 10 things. And then if you really need to reference them, then you'd use indices or something like that. Okay, so any questions? This is the end of the slide portion. So this would be a good time to ask if you have any questions. Okay, I'm not hearing any. So I guess I'll move on to the profiler itself. Okay, I'll share the other screen. Okay. Right. No, sorry, wrong code. That is XFL code. Hopefully this one, maybe it's not, just it's weird. Okay. Okay. So does this show up? You should be seeing the Legion website.
Yes, we can see it.
Okay. Right. Okay. So the Rust profiler is basically feature complete from the perspective of basically everything in the original Python code that does not require Legion spy. So basically all of the utilization for processors, channels, memories, all the detailed views for processors, channels, memories, all of those are implemented and they're all bitwise identical. So I guess the good thing about the profiler at this point is we're pretty sure that's correct. And it should have basically indistinguishable performance from Python. It's running in the CI all the time. And so I'm pretty confident in it. And so, if you want to install it. These are the instructions. I won't spend too much time here because you can read this on your own. But if you want to look at the code, we can jump over to GitHub. This is on master. And so inside of the tools / Legion Prof RS directory, we have all of the Rust code. And so I guess at this point, I was basically going to go through a tour of this code to basically give you an overview. So hopefully, if you need to make changes, then you'd have a sense of where to start. So this is basically the top of what Rust calls a crate. It's not quite an object file in the sense that C++ would have, but you can think about this as this would be the unit that would go into an SO. Right, Rust doesn't quite have that notion in it, but that's sort of the closest analogy. So Rust uses a build system called Cargo, which I actually think is really nice. And so basically all of the build rules and stuff are all declarative. And it's mostly rather than being this is a declarative system, so this is not a shell script. Right, it's not executed, but it basically specifies, here's the name of the thing, and this is the version number, and here are all the dependencies and their version numbers. And as a general rule in Rust, everything is supposed to follow semver. So I could say, Serde version 1.0, and Rust knows, it can go up to anything below 2, right? Typically, is supposed to be compatible. And so when you build it, it will download and it will fetch and it will build all of these dependencies for you. So that's one of the really nice things. So we have like a command line parser, we have a CSV parser, we have some sort of utility features, and this is a zip implementation, so gzip, and a parser, and more enum utilities. And this is a multi-threading thing. So we have multi-threading in here. And more serialization, right? So we can pull in all these dependencies and it's basically seamless, which is really nice. Okay, so popping back up here, all of the actual source code is under source. And if you look, like 99% of Rust projects are organized the same way, which is nice. So if you learn this once, you will know it for every code you ever look at. So almost every Rust project is organized the same way. Main is the executable. So this is where main is going to be defined. And then lib is essentially the library entry point. And so in this case, we have both. Not every Rust code is going to have both, but we have, this is basically, it's divided between a library component and an executable component. And I guess I'll just open this. Okay. And so here's the executable component. This is main. Is just sort of minor complications on top of what I showed you. Here's all the argument parsing goo, which you don't really need to care about. It's a little bit verbose, but it handles it for you, and then you don't need to think about it. It gives you all this nice stuff. And so sort of in terms of the core functionality, it's really starting here at state. So the way that the Rust profiler is organized, it was originally written sort of as direct a port from Python as possible. So Python has a state object, Rust has a state object. And sort of to a first approximation, if there are methods and they're the same between the two, they're named the same way. But there are some differences. So basically, when we run through a profiler, we're going to run through a series of stages. So first, we're going to build this state. We parse the file names, we parse all the files. So that deserializes the file here. That produces the way that this is set up is deserialization provides a set of records, and then the state processes the records. And so the cool thing about this is actually going in parallel. That's one line of code to get you parallel execution, which I think is really cool. So we actually parse these files in parallel. But at any rate, we process the state. At this point, the state is basically complete. We do a couple of extra stages. We do trimming. We do sorting. This is equivalent to Python. So if you're familiar with the Python code, this is basically the same stuff we do in Python. And then this is the function that basically spits out the state, the HTML visualization file. And one thing I'd like to point out here is this reference here. That is an @ or ampersand, not mute, right? There's no mute here. And so that means, you know, just from looking at you don't even need to look at that function or anything that it calls. You know that the state is not modified at this point, right? So everything that modifies state is up above, right? So these method calls, those can modify state. But when you go into emit the visualization, you know state is fixed at that point. Okay. Any questions at this point? Okay. So I'm going to jump over. Let's look at the serializer first. Okay. So, so those of you who know, the Legion, profiling format know that they're basically, it spits out, these records, right? The format is basically a sequence of records. The records have some binary format. There's a little bit of goo at the top of the file that says, here's the different record kinds and what they contain and their data types and so on. This code is basically copy and paste. It not literally, I mean, there are some things that I changed here, formatting and syntax and stuff, but to a first approximation, this is copy and paste from that format, which I think is really cool, because that means that you can immediately diff, if the Legion Prof format changes, you can immediately see what changed here, right? And these records correspond one-to-one with what occurs in the log file, so you always know, what you're looking at. So basically, the purpose of the serializer is to reconstruct these records. And what it's going to return at the end is basically a list of them. And so we don't really need to go through this code because it's not actually that important, but just sort of keep in the back of your head, when we come into state, what we're getting is essentially a giant vector of all these records that, describe the contents of the log file that we parsed. Okay, so then in terms of like what is actually the core of the profiler, that's all going to be in state. So this is the state object and all the methods that are associated with it. If you're familiar with the original Python code, there are a bunch of classes like processors and memories and channels and tasks and so on. Those all go in here. But I'm going to start from the bottom, jump to the bottom. This is probably also the longest file. Okay, struct state. Okay, here's state. That is all the stuff that goes in the state. And so this captures literally everything in the entire profile. Okay, so there are no inter-object references. There is no object graph. So we don't have an object soup. That was sort of one of the biggest things that, in terms of effort to decode the original Python code, was to figure out how those objects were actually related and what actually mattered. And so, one of the key things here is that this owns all of the data. So all of the data is owned through here. And so one of the tricky things is, because we do not have references, how do you keep track of, where an object is, right? Because in the original code, you'd have things like, a task would be stored in a list on the processor, and it would also be stored in an operation map on the state. And so the decision that I made when designing this code is that everything gets owned by the processor or the memory or the channel. So processor contains all the tasks. And so that means when you're in tasks or when you're in state, if you want to look up a task and you don't know what processor it's on, what you have here is basically an index. So this is a map from, a task is identified by an op ID. You look up that op ID in this map, you get the processor that it's on. And then you could jump over here to the processor, you get the processor from the proc ID, and then the processor is going to have the map from op ID to task. Okay, so that's sort of like the basic pattern in all this code. So if we jump over to proc, okay, this is the processor. Okay, so like I said, processor owns the tasks, right? So this task object here, that's going to contain all of the actual data. In Python, you had class task that corresponds to the struct task in Rust. And notice this is not a reference. That means it's owned. So processor is always sort of the definitive place to find the task. One of the other things to notice about this is I decided to not box anything. So one of the things about the Python code is because everything's a reference anyway, you can sort of mix things up in these heterogeneous lists. So you can have, the processor has a list of tasks, but it also includes meta tasks, mapper calls, runtime calls, profiler tasks, and so on. In this code, those are all separate. So we have one map on tasks, one for meta tasks, one for mapper calls, one for runtime calls, and one for profiler tasks. And so that has the advantage that they're all maximally dense. So right, this is going to be basically a dense piece of memory, contains all the profiler tasks. And so hypothetically, that makes it, efficient. When you're trying to do sorting or whatever, you can fly through all those tasks and it's all cache efficient and stuff like that. It does mean, one of the big caveats is that it does mean that there are cases where you have code that looks like it's done multiple times. So, here's sort of the big example of that. This is code that basically exists to deduplicate some of this code. This is essentially Rust's version of a switch statement. And so depending on what case you're going down, you're going to get a task, and you can see that the code here goes and says, look up the task in this data structure, and return some things, right? So you do end up with some of that type of code. But the advantage is when you're doing things, for example, just for runtime calls, you can just fly down that list and it all works. So that's sort of the nice part about it. Okay. Right. So I guess as sort of a high level structure, if you're used to the Python code, things roughly correspond. So Python had a trim time range and Rust has a trim time range. It does basically the same thing. Rust had a sort time range, or Python had a sort time range, Rust has a sort time range, right? So if you're used to the Python code structure, all of those things basically correspond one-to-one. And so hopefully there are no real gotchas there. I mean, obviously the implementation is different, but that should hopefully be all that you really need to know about that. Right. What else? If you have questions, now would be the time.
Any questions for Elliot?
Or else I could go on to the visualization code.
Why don't we go ahead and do that?
Okay.
Does Rust have any templates? Yeah, does Rust have templates to like?
Rust does, yes.
You could have templated some of those like repetitive for loops and stuff.
Right. In some cases, you could do that. Let me see. I think there are a couple here. Right. Templates. Okay. So this time point, let me find struct time point. Okay. So time point is a templated struct. Okay. So this is, a struct can, templated on two things. Right. These are the trait bounds. This says, this is basically, is trivially copyable. Is effectively what that means. And so this was an example where, I went to the effort of doing that. I think, unless something's sort of duplicated at least a couple of times, it's generally not worth the effort to do the templating, in my opinion. But yes, Rust does have templates.
Well, do they have standalone template functions?
Right. So, yes. And I was looking at one just a minute ago. I think we've got one here. Here. Yes, that's an example. So here's a function that's templated. So template argument, use it in the type signature, and then here's the constraints.
Right.
So yeah, you can do that.
Okay. I'm kind of surprised you didn't do that over there. We had a bunch of loops that all were doing the same thing, just different types.
Yeah. So
match is
yeah, I will
dispatch,
not.
right?
What's that?
The match thing is dynamic dispatch, not static. Right.
That is true. Yeah. So the match part.
Oh,
right.
okay.
This part is dynamic. So basically, think about this as you're getting a union of all the different types, and then it's basically blasting.
Well, yeah, I know what a match statement is.
But you're probably thinking of this code.
Yes.
Yeah. So this stuff, where I'm doing, the same thing, 3 times in a row, that could be factored out pretty easily.
Yeah.
It's a little bit more tricky up here because this is a different container. So, I mean, one of the things that's tricky is depending on what type you're looking at in this, where'd it go? Yeah, these are different types. So this is, tasks are a map, meta tasks are a map to vector, and mapper calls, the other kind of calls are all vectors, right? And that all has to do with how things are keyed, right? So tasks are uniquely identified by their op ID. Meta tasks are not uniquely identified, but you can look them up based on whatever, right? So I will not claim that this code is sort of maximally deduplicated. So there may be more opportunities to sort of and I think part of the reason why it's written this way is it was initially sort of pointedly direct translation, right? I mean, it was rewritten in this sort of different style, but it was very much not trying to change around a bunch of stuff so that you could see the correspondence between the code in case things were off. And I think now that things are sort of bitwise identical, there's more room to come back and say, like, do we really need to look up meta tasks? Like, if not, then it would be a whole lot easier just to stuff that in a vec, right? Because you don't actually need to look it up. But it depends on what use cases you have, right? So, yeah, right. So there may be opportunities to come back and clean things up still.
One last dumb question. Are the bangs macro expansions?
Yes.
Or is Rust macros hygienic?
No, they're
It's okay if they're not. I'm just curious.
They're not. Yeah.
Okay, so like C macros.
Well, it's a little bit complicated because Rust has 2 different macro systems. And I think, yeah, right. So I think there's sort of a simple pattern matching type macros, which I think are actually hygienic.
Okay.
Hygienic-ish. But then there's a more powerful sort of general purpose macros where you actually write, in Rust code, arbitrary processing. It basically think about token stream in, token stream out. So it's not quite strings, so you can't butcher it quite so badly as you would for, C macros, but it's still, you could manufacture a variable name for anything, right?
Okay.
So, yeah, right. So that's just sort of one, yeah. If you're actually writing macro code, you do need to watch out for that.
But the bang is just a macro invocation.
Yeah, bang just sort of signals to you that it's a macro. So it's just obvious at the call site. So yeah, so the visualized
That's required.
code,
That's required, or is it?
well, it's part of the
commission?
name. So,
Okay.
I mean, I don't know whether they would ever like loosen this, but this is write bang is actually the name of this thing. So it's not bang. Bang is not an operator here. It's actually a symbol in the name, and the name is required to end in a bang.
Oh, for a macro. Okay.
For a macro, right? Yes.
Yeah. Okay.
Right. Yeah, right. So all this stuff, so here's a macro. This is reading from the file system. right? So when at build time, it will go slurp that file, shove it into a string, and store it here. Right. So what is that sort of, allows the binary to be self-contained, right? So the binary doesn't have to go read that. Okay. So, again, feel free to stop me if you have any questions. So, right. So conceptually, right, what state does is it basically builds that struct I showed you, this is the state with all the processors, memories, channels, and all those, tasks and, copies and so on, all go in here. At that point, when you have that state built, and you've gone and you trimmed the thing and you sorted it, then you kick it over to visualize. And basically we jump down here. Okay, emit interactive visualization. It takes the state, where you want to spit out to. Do you force an override, right? And this basically spits out all of the visualization code. There's sort of one other sort of language level thing to pay attention to here, which is that we have a result. Okay, so result, one of the things in Rust is Rust has no exceptions. And that means everything you do that could error comes through a return code. And so, I mean, one of the nice things about Rust is that, unlike C, if you have a call that to something that's potentially fallible and you don't deal with it, then the Rust compiler will throw a warning at you. So if you read all your warnings, and there should be none in this code at this point, then you will know that you've handled all the possible errors. But it's still a pain, to write code that says if, this call succeeded, then, whatever, otherwise abort, right? And so Rust has this question mark operator. So if you call this is something, doesn't really matter what it does, this is writing to a file or whatever, that could potentially fail. And if it does, then this question mark operator basically immediately returns. So it's sort of passing along the error up the chain. And that's sort of, something we'll see, in a lot of this IO type code, write and then question mark to check the error, create something, then question mark, check the error. So a lot of these calls, you'll see that all over the place. So, right. Yeah, so I guess, the other stuff that's worth looking at is this code is code that deals a lot with serialization. So a lot of this stuff, you're iterating over the processors. So this is sort of the style of a lot of Rust code here. So we have processors, that's a list of things, list of procs. We iterate it, this says parallel, but that doesn't really matter. That's sort of functionally equivalent to sequential. You can chain your operators. So this is a filter, as long as it's not empty, then for each one you map, and then you're going to run this function on that. And then in the end, this is basically saying, give me a B-tree map of all the things. Okay.
Hey, Elliot, quick question about what are the semantics of the parallel iteration? Is it just a classic data parallel you can assume no ordering?
Right, I think so.
That? Okay.
Right. Yeah, so I think one of the nice things about Rust, so obviously it's not going to track IO types of dependencies. So if you do IO, then you're sort of on your own in terms of figuring out that things are independent. But one of the nice things is that it does actually check that the references that go like into these closures. So this is the closure syntax with vertical bars. So when we capture this proc, that the references are not conflicting, right? So either they're all immutable, or if they are mutable, then you're sort of doing an element-wise thing. So each thing you modify on its own. And so Rust's type system is actually powerful enough to check that. And so sort of a lot of the data, data races, classic data races you just can't get in this framework by virtue of the Rust type system. Okay. Right. But then I think, the other interesting piece of this is if we jump up, so this calls basically emit TSV on a proc. We go to emit. Must be, yeah. Right. So here's this, again, this is, that's something that's templated. So here's sort of how you write with a CSV. This is using a CSV library to, to spit out some of these files. And then for every point, right, this is basically going to spit out a series of points. For every point you spit that out, this is passing F, which is the CSV writer. And if we go point, look, yeah. Right, here's the code that basically spits out the CSV entry. And if we do, it's doing a bunch of processing, which again is slightly ugly because of the different cases we have in the processor. Okay, but here we have the data record. So that one of the nice things about Rust is it has these sort of pre-built serialization libraries. And so Rust knows how to serialize this struct. So when you spit this out, these are going to get spit out into the CSV fields. So each one of these things gets, one column each type of thing. And then here's the serialize call. And so you're going to basically serialize a set of rows. Right. The other thing that might be nice to look at is if we looked at the data record. Okay. So this is the serialization I was talking about. This derive here, if you're familiar with Pascal, it has sort of equivalent semantics. So basically serialize is a trait. It's like an interface. So it's like basically Rust knows how to serialize this type. It has a serialize method or whatever. Derive says automatically generate the code for this serialization. And that's going to run a macro that's actually going to inspect the contents of this struct. And for each of these types, based on what it is, it's going to automatically generate the right code for it. And, and when it works, it's great. And when it doesn't work, if you need to do something custom, then it can be a little bit more work. So here, for example, some things we want to spit out to a certain number of decimal places. And there's a little bit of jumping around we have to do upping this count, to spit things out in the right format. Okay, so it can be a little bit ugly if it doesn't do what you want, but when it does do what you want, it's great because you save a bunch of work in the serialization code. And I think that's it as far as sort of basic stuff goes. So I know that was a lot. That's part of the reason why I wanted to record it is you can come back and review this. If for some reason you need to modify the code in the future, you can remind yourself what's in there. But if there are any other questions right now, I'd be happy to take them.
So like, if you were to do the critical path analysis, right, then you are going to have to build like a graph like data structure to do that analysis. Right, and Python does that in your standard way of nodes and edges and stuff like in the heap, which Rust is probably not going to be particularly happy about. So what would your architecture look like for doing that?
So I would go with, if you think about this sort of like a database, right? You have tables and you have foreign keys, right? So if you're trying to build like a critical path type thing, basically you're working with foreign keys. And that's basically like what you have here, right? Is like a little table that helps you get from this to this. And so it's not fully fleshed out right now because it's not necessary in the current generation of the code. But if you needed the ability to go from any op ID, to find out what it is, then what you'd basically need is a new table effectively in this relational data structure that tells you, how do you look up the XYZ thing, based on some arbitrary ID.
Can you have like multi-map relationships in these? Like, does Rust have a multi-map? kind of-
you mean like multiple entries per key?
Yeah. Well,
Yeah.
yeah.
Or you mean heterogeneous in the sense that, it's not every key is of the same type.
No, I meant multiple values per key.
So in that case, I'd go, if you remember the struct proc bit, this is how I'd implement it, basically map to vec, right? This is a poor man's multi-map, right?
Sure, yeah. It's
Not necessarily
completely
super pretty.
memory
Yeah,
or
I
memory
don't,
efficient. Yeah,
I don't know that Rust has a direct,
like C++ has the standard multi-map data structure that you can
Yeah.
use, but
it's possible that they do. And if it's not in the standard library, it might be in a third-party crate. But I just haven't tried that hard to look for it.
yeah, I'm just thinking about how to represent the graph, like all the
Yeah.
edges and stuff.
Right. Right. Yeah. I mean, I think I'd be inclined just to start with a basic, map to vec. And in my experience, Rust has been efficient enough that it hasn't been worthwhile to really push on any sort of low-level optimization. But yeah, I think in terms of the basic architecture, you'd use the same basic sort of index structure and IDs to find things.
Does Rust have any like libraries like lenses and Haskell that make it easier to pass like lots of parameters to your functions?
I don't know off the top of my head, but the
I can just
Rust,
see that becoming a problem. Like once you start having like these giant lookup table or lots and lots of lookup tables that you've got to pass through
Mhm,
for different kinds of relationships, then you start accumulating, right?
mhm,
Lots of arguments in your functions that you're typing out all the time.
right.
Like,
Yeah, I mean, I haven't had too much of an issue with that, but I could imagine, I think, yeah, I mean, you could make a struct, right? A struct can contain references, and the
Right.
references would be safe. So in
Yep.
terms of features, I think it's all there. But if you're asking about how to make it pretty, I'd have to look. I don't know off the top.
I'm just
of my head.
wondering how hard it's going to be.
Right. Yeah.
It's not that I don't believe that it can't be done. It's just how ergonomic have they made it?
Mhm.
It took Haskell a while to come up with the lenses library, too.
Yeah, I mean, I know, there's quite a bit of overlap between the Rust and Haskell communities, so I'm sure the Rust people are aware of it. But yeah, I'd have to look to see, what actually exists. Yeah.
Is there any kind of REPL or interpreter for Rust, or is it always compile time?
I'm not aware of a REPL.
Okay. Let me actually ask my real question, and then maybe
Go ahead.
I was already presupposing one answer, which is if we wanted to have some sort, you were making the point that this thing is now basically a database, and one of the things we can do is we can run reports on it, like generating the visualization data files. But if you wanted to do kind of more interactive data mining, what I'm wondering is that, do we have to invent some SQL-y DSL for performing queries on this thing, or is there a way for people to write little snippets of Rust code that directly interact with the data structure? That seems closer to the metal, if you will, and therefore preferred if it's possible.
Mhm. Yeah, I mean, I'm not aware of anything off the top of my head. But who knows? Yeah, I mean, it could exist.
I guess so. You said that this thing is mostly built as a library, so in theory, maybe you're just writing your own little Rust application that links this library, and then, well, okay, we don't have a permanent version of the data structure, right? You built it
Right.
up.
Yeah. I mean, yeah, right. If you could get a copy of the data structure into memory in an executable, then you could basically do whatever you want with it.
Okay. Does Rust have a simple take this whole state object and dump it into a file in the most efficient Rust way possible?
It does, right? I mean, that's sort of what some of the visualization stuff is, right? With this serialize.
Well,
So I think,
that's custom serialization formats. I'm looking for the pickle equivalent.
well, yeah, I mean, this is essentially pickle. Yeah, I mean, so this stuff, that's the custom one. But
I
this
see.
one here, that's sort of the just do the basic thing. And it just turns out that the basic thing is really similar to what we need. So that's good enough. And we don't need to think that hard. Yeah, the one thing is that the code is, let me see. Yeah, actually, I think this is fine. So basically, I mean, if you went through here, you'd have to add like serialize to a bunch of this stuff. But once you do that, then you can serialize it into basically any format you want. So if you want JSON or you want message pack or whatever, you know, the new Vogue thing is, you can spit out basically any data format once you implement the serialize trait.
Okay.
So yeah, that part would probably be easy. Yeah, and it would be like 10-ish lines to sort of deserialize it and, you know, get something going. So not zero effort, but not a huge amount of work either.
Right, and then, but it would have the cost of, you do have to haul the data from disk to memory for
Right.
each new query.
Yes, yes.
Okay, so it's good for kind of, if you get to the point where you have a query that you're likely to want to run, you know, on each new profile you generate, then that's a relatively efficient way to do it, but it's not good for the initial exploration
Right,
approach. Okay.
right.
It looks like there's a REPL called Papyrus, but it's not clear if it's fully functional or not with everything you could do.
It seems worth trying out.
Okay, cool. Well, thanks for doing this, Elliot. This is it's a big enough blob of code that it was a little daunting to just kind of jump into it myself. So.
Yeah. Okay, so yeah, I guess if there are any other questions, you know, feel free to ask them, you know, or I could release the time and we can, you know, go on to something else.
Okay, let me ask one other question. So you spent a bunch of time basically making Rust equivalents of C++y things, you know, basically the stuff that dumps the state in the first place. How scary would it be to go the other direction, right? Taking C code and putting it in Rust seems like it takes off all the seatbelts that Rust is so carefully produced, but is there a story for taking Rust crates and using them from C++ code?
There is, I'm not necessarily super familiar with it, but I think if you want to expose a C API, there is sort of a standardish way to do it. And I don't think I've tried it myself, so I don't know off the top of my head how much work it really is. But I think, you know, you can do that with some modest amount of effort.
Okay, I'm just wondering if you know, in some future world, if we want to make changes to the profiling stuff that involve changing what's dumped as well, it'd be nice if there was one library that was both sides of it instead of a C++ and the Rust thing we have to keep consistent.
Yeah.
Any other questions or comments? Okay, well,